Okay, in this video we are going to continue with assignment 8 from my Calc CD class, multivariable. We are doing double integrals in polar. We're really converting from rectangular to polar and then evaluating the integral. Let's do it. So first up we have the integral from -2 to 2, 0 to square root of 4 minus x squared of x squared plus y squared dy dx. All right, step 1 is to look at the integral and pull the bounds off, right? So I know my x bounds and I know my y bounds. I will then use those to create the region in the xy plane. So x goes from -2 to 2. Y goes from 0 to the square root of 4 minus x squared. That's a semicircle. So I'm going to draw a semicircle with a radius of 2. And I know because x goes from -2 to 2 that I want the entire thing. It's really important that you realize that step. So we have the bounds. You take those, you write them down. You create the xy region. Then you just describe that region using polar. There isn't like a one-to-one correspondence, I would say. Like, these are the bounds, I'm just going to like use formulas and get it. You have to kind of look at the region. So I can see that r goes from here to here, so 0 to 2. And I can see that theta is going from here to here, so 0 to pi. I know that the integrand, which is going to be x squared plus y squared, is just r squared. So I'll set this up. So we're going 0 to pi, 0 to 2, the integrand is r squared, and then there's always r dr d theta. So the place where this could go wrong is you forget r from r dr d theta. Don't do that. Can't stress it enough. Remember, there's an extra r. This we can break into a product of integrals, so I'm going to do that. 0 to pi d theta, 0 to 2 of r cubed, integral of 1 d theta is theta, from pi to 0 is just pi, 1/4 r to the 4th, 0 to 2. So this is going to give us 4 pi. Let's look at the next one. We're going 0 to 3, 0 to the square root of 9 minus y squared. You're going to run into a lot of semicircles when you do this. So that's a semicircle. Square root of x squared plus y squared, dx dy. So dx dy, you got to look alive on those. You got to make sure that you're getting these right. So the y bounds are from 0 to 3. The x bounds are from 0 to the square root of 9 minus y squared. Okay, so you're probably really familiar with, when y is equal to the square root of r squared minus x squared, or y is equal to the negative square root of r squared minus x squared. That's like the top and bottom of a semicircle, of a circle rather. The semicircle on the top, the semicircle on the bottom. For y, for x is equal to the square root of 9 minus y squared, you're probably less familiar, but if it's the positive square root, it's the right side. If it's the negative square root, it's the left side. So in this case, we get the right side. Actually, I think you would have gotten this right no matter what, because the positive and the negative kind of like overlap in the first quadrant, sort of. No, that's not even true. So yeah, you would have gotten it wrong. Well, maybe. I don't know. Here's the region. So x is definitely greater than or equal to 0 is kind of the point. So we're just going to have our circle, our semicircle, and then y goes from 0 to 3, so just this top part. So r is going from here, which is going to be 0 to 3. And then theta is going here, which is going to be 0 to pi over 2. We have to convert the integrand, which will be the square root of r squared. R is positive, so that's just r. Set up our integral. There's going to be r for the integrand. There's going to be r dr d theta for our dA, the area element. We can break this up, so let's do it. And then integrate. So we'll get pi over 2, and then 1/3 r cubed from 0 to 3. So we're going to get 9 pi over 2. All right. So you can always slow it down, rewind it. I'm going to try to go a little quicker through these because we're really just doing problems at this point. Hopefully you've got the idea and you're just like with me for more practice. So, all right, on this one, we're going 0 to 1/2, root 3x to root 1 minus x squared, x dy dx. So our x bounds are from 0 to 1/2. Our y bounds are from root 3x to root 1 minus x squared. Okay, we got to really deal with this. So we got this. And then I know that x is just from 0 to 1/2, really. This is our semicircle, so I'm going to draw that. Semicircle radius 1. And then the square root of 3x is just a line with a slope of root 3. So because of that, I know that y equals mx. The slope is the tangent of the angle. Like I actually know where these intersect because the slope is root 3, which means that the angle is pi over 3, which means the ordered pair is 1/2 root 3 over 2. X is going from 0 to 1/2. So that was important because if X was going from 0 to 1, I guess this region would be very complicated and like not easily expressible. But it would be the other part of the circle. And there would be more. It would have to be like the sum of two double integrals. But since X is going from 0 to 1/2, that's the part that we need. All right, so this ordered pair, well, R goes from 0 to 1, obviously. I do know that I'm going from that line to that line. This ordered pair is definitely 1/2 root 3 over 2. So you could take 1/2 and plug it into the line or the semicircle. Either one is going to give you 1/2 root 3 over 2. You could use the fact that the slope of that line is root 3, which means the angle itself is just pi over 3 and not even really know the ordered pair. It's up to you. There's a lot of ways you could do it. But that angle is definitely pi over 3. And then you're definitely going to pi over 2. All right, so let's change the integrand, which is x. X is our cosine. So that's just going to be this. Set it up. We have pi over 3 to pi over 2, 0 to 1, r cosine, and then there's going to be another r, dr d theta. We can split this into a function of r times a function of theta, so let's split the integral. And then let's just do it, right? The antiderivative of cosine is sine, and then you get 1/3 r cubed. And then fundamental theorem, this thing, you got to remember some values. Sine of pi over 2 is 1. Sine of pi over 3 is root 3 over 2, which you can see from the ordered pair. And then we'll just get 1/3 here. And I don't really think the answer gets better, but it would kind of simplify to this if you think that that's simpler. All right, let's look at the next one. 0 to 4, 0 to square root of 16 minus x squared, tan inverse of y over x, dy dx. So as usual, we just pull off the bounds. X is 0 to 4. Y is from 0 to the square root of 16 minus x squared. Again, a semicircle, like by far the most common curve that you're going to run into here. Let's sketch our region. So since x is only 0 to 4, we just get the first quadrant. And then it's there. So r goes from here to here from 0 to 4. And then theta is going to be 0 to pi over 2. Okay, we need to convert the integrand. So this is the first time we've run into this in this video. Probably not in your notes, but in this video. So one formula that is important that we haven't used yet is that tan of theta is y over x. So that means that theta is the inverse tangent of y over x, which means our integrand here is just theta, which is good because it's simple. Let's write this down. So 0 to pi over 2. 0 to 4, theta, then we pick up an r, dr d theta. We can split this, and so we should. Here we have this. So this one's interesting because you just get 1/2 theta squared from 0 to pi over 2, and then you get 1/2 of r squared from 0 to 4. So when you plug in pi over 2, you get pi squared over 4, so that'll be pi squared over 8. And then when you plug in 4, you get 16 over 2, which is 8. So the answer here is just pi squared, which is kind of neat. Let's look at the next one. How many more am I doing? I guess this 1, 2, 3, a couple. All right, here goes. 0 to 5, 0 to y, x dx dy. Okay, there's nothing unusual about this. First, our y bounds are 0 to 5 and our x bounds are 0 to y. I prefer to think of that as y equals x, even though it's like x equals y. Sketch the region. So y is going to go from 0 to 5. So we just have like a line up here. And then x goes from 0 on the left to y on the right. So y equals x looks like this. Our region, because x is going from 0 to y, is going to be this. All right, so we just need to describe this in polar. It's not like a super nice polar region, but that's okay. This equation is y equals 5. Y is equal to r sine of theta. And so that equation in polar is 5 cosecant theta, which is important because r is going from 0 to that line. So r goes from 0 to 5 cosecant theta. Simultaneously, the 0.55 is definitely on theta equals pi over 4. So if we're going from theta equals pi over 4 to pi over 2. All right, the integrand, which is just x, is going to be r cosine because x is r cosine. We can write our integral. We cannot, don't forget r dr d theta. We can't in this case separate it because the bound for r depends upon theta. So we have to actually like do this a step at a time, which is worse, but probably should be more common. So this is what our integrand looks like, or the whole integral, I guess I should say. First, we integrate with respect to r, right? So we're going to get pi over 4 to pi over 2. You'll have 1/3 r cubed, and then cosine of theta. R is going from 0 to 5 cosecant of theta. So we make the substitution. We get 5 cubed is 125. So you have 125 over 3, pull it out. You have cosecant cubed times cosine. I think the best thing to do here is switch to all sines and cosines. So I'm going to take cosecant. Cosecant is 1 over sine, so it's really just cosine over sine cubed. So we have this. Let u equal sine, and then du is going to be cosine d theta. So really it's just, it's u to the negative third, right? So plus 1 times the reciprocal is going to be negative 1/2 sine to the negative second. So negative 1/2 times 125 over 3 is negative 125 over 6. And then you get sine to the negative second, so I'm going to write 1 over sine squared. Pi over 4 to pi over 2, we just got to plug in. So the sine of pi over 2 is 1. The sine of pi over 4 is root 2 over 2 or 1 over root 2 because we have to square it. So 1 over root 2 squared is 1/2, and then that's in the denominator, so it goes up as 2 in the numerator. Happy to explain any of that in the comments if someone has a question. So this will give us 1 minus 2, which is positive 125 over 6. So that's our answer. All right, 12, 13, 14. I got 3 more to go. I'm going to actually use a calculator to evaluate them after we set them up, so these might go a little faster. All right, 0 to 2, x to root 3x, y dy dx. So these, you start to see things over and over again, right? Root 3x, we know is pi over 3. We've run into it before. All right, pull off the bound. 0 to 2, x to root 3 over x. So this is going to be a weird, well, it's not a weird region. Like, it makes sense. I'm going to graph both of those lines. So y equals x, and also y equals root 3x. I need to figure those out in polar. And then x goes from 0 to 2. So you kind of like just close off the region there. We're going to need to convert that line into polar. But this is our region. Okay, so you go from 0 to x equals 2. But x equals 2 is not a polar equation. So we need to convert x equals 2. X is our cosine, which means that r is 2 over cosine or 2 secant. So we're going from 0 to 2 secant. And then theta, well, what are those lines in polar, right? So y equals x is definitely pi over 4. And then root 3x is definitely pi over 3. So we're going from pi over 4 to pi over 3 as we rotate through. All right, so then we can set it up. We need to change y into polar. So y is just r sine, so we get this. So our integral will be our bounds, and then r sine of theta, r dr d theta, and then I use a calculator to do this because this is taking forever. So I got that. I think you can definitely do this by hand without like too much trouble, but you know, this was taking me ages, so I decided to use a calculator. I don't know if your teacher will allow that, but sometimes you just gotta move on, you know? All right, negative 1 to 2, so that's going to be weird. If it's not symmetric, you kind of know it's going to be weird. 0 to the square root of 4 minus x squared, and then x squared plus y squared, which is just r squared, dy dx. All right, so first pull off your bounds. X is going from negative 1 to 2. Y is going from 0 to the square root of 4 minus x squared. So we got like our semicircle, but not all of it, which is annoying. So we got this. But x only goes from negative 1 to 2, which means this is our region. I don't think there's any way to do this in one shot, so I'm going to have to do 2 integrals and add them together. I'm going to split it right there. That point should be negative 1 root 3 if you plug into the semicircle. So that's unfortunate, but not terrible, because if I divide everything by 2, I'd have negative 1/2 root 3 over 2, which is a unit circle point. So I know the point at least. So this negative 1 root 3 becomes negative 1/2 root 3 over 2, which is 2 pi over 3. So I do know the angle at least. So we're doing two separate things. So for the first part, theta goes from, r goes from 0 out to 2. And then theta is going to go from here to here. So theta is only going from 0 to 2 pi over 3. That's one integral. And then for our second region, which I've highlighted in a slightly different color, r goes from, apparently I'm writing that integral now. Okay, so x squared plus y squared we know is r squared. And then r dr d theta. Going to use a calculator on that. Okay, so for the second region, the triangle, we have r is going from 0 to x equals negative 1, which is not in polar, so we need to convert that. X is r cosine, so r is negative secant of theta. So our bounds are going to be 0 to negative secant of theta. At the same time, theta goes from 2 pi over 3 and then ends at pi. So that one's straightforward. Let's write that integral. The integrand is still just r squared, and we still pick up an r dr d theta. So we have these bounds, r squared, still an r dr d theta. I use a calculator to just get this answer. I got 8 pi over 3 plus root 3 over 2. All right, let's take a look at one more in this video. So we're going 1 to 2. So again, I'm expecting this to be weird because those aren't symmetric. And then 0 to the square root of 2x minus x squared of 1 over the square root of x squared plus y squared dy dx. So that upper bound for y is still a semicircle. It's just a weird semicircle. But if you do enough polar, you will run into that frequently, and you might just know what it is, which I recommend. But otherwise, I'm going to show you how to convert it. So our bounds are x goes from 1 to 2, y goes from 0 to this weird radical thing. So let's look at that. Y is equal to this, so we could square it. We could move x squared over and move everything over. I'm going to complete the square. So add 1 to both sides. I get x minus 1 squared plus y squared equals 1, which means it's a circle of radius 1 that's centered at 1, 0. And because it's y equals the positive square root, we just get the top. So really, we just have this. But because x is only going from 1 to 2, we don't have the whole thing. We just have this part. So annoying, but it's okay. R is going to go from there to there and there to there. So the first curve that you hit is x equals 1. The second curve that you hit is just r equals 2, right? That one's easier. So x equals 1, we know how to convert this. R cosine is equal to 1, so r is equal to secant. Okay, so our r bounds go from secant of theta to 2. Nope, not to 2. That's not 2. I was fooled, right? That is a circle centered on the x-axis with a diameter of 2. That is 2 cosine of theta. That semicircle is 2 cosine theta. So we're going from secant of theta to 2 cosine of theta. That's a big one. I have many videos talking about how to deal with that. So if you have a circle centered on the positive x-axis, it's diameter cosine. Negative x-axis, it's negative diameter cosine. Positive y is diameter sine. Negative y is negative diameter sine. Got to know those. They speed things up. All right, so these are our bounds. Secant of theta to 2 cosine of theta. And then theta is going to rotate until you hit this line, which is definitely pi over 4, right? So we're rotating from 0 to pi over 4. So let's convert the integrand, which is going to be 1 over the square root of r squared, so 1 over r. And then our bounds, our integrand, and then there's an r dr d theta. So we get this. So we're really just integrating 1 dr d theta. I still use a calculator, and the answer is gross. I did it like multiple ways to like confirm my answer. So one tip on these is if you just straight up punch the original integral into your calculator, it can probably evaluate it. And then you put your polar integral in and you just see if you get the same thing. I got two answers that looked very different from each other, in my opinion, but they were the same numerically. So I got 0.53284 or either of those weird things with natural logs. Anyway, I'm going to stop this one here. I'll be back in the next one to finish up this problem set. I hope this was helpful, and good luck.